Hi and welcome! Have you ever wished you could build your own expansion card for your vintage PC? If the answer is yes, then you will probably find this video interesting. We're going to build a simple yet functional 8-bit ISA card using a Raspberry Pi Pico. In case we're not familiar with it, the Pico is a very affordable microcontroller that has plenty of CPU power, tons of GPIO pins, and even a USB interface. So let's get started. A while back, I designed a very simple PCB for the Raspberry Pi Pico that simply connects the Pico's GPIOs to the ISA bus. Since the ISA bus operates at 5 volts and the Pico GPIOs at 3.3 volts, we need to connect the two via bidirectional level shifter ICs, which are the only ICs on the board. This board also needs a name, so rather predictably I named it ISA Blaster. The idea is that if the Pico is fast enough, it could talk to the ISA bus without the need for additional hardware, like latches, buffers, or logic, and that would allow us to build a very affordable 8-bit ISA card that is completely software controlled. The 8-bit ISA bus has 62 bits in total, 31 on side A and 31 on side B. This includes 19 address pins, 8 data pins, 6 IRQ pins, several control pins, some power pins, and a few others. But in order to build a simple DOS I/O device, we don't need all of them. We should be good with just 12 address bits, 8 data bits, 1 IRQ that the user could select with jumpers on the board, and at least 2 control pins for I/O reads and I/O channel ready. This is a total of 23 pins. The Pico has 26 GPIO pins that are available for us to use, so we have a few pins to spare that we could use perhaps to connect to other control pins to make the board more versatile. Moreover, the ISA bus operates at 8 MHz, while the Pico has a clock frequency of 133 MHz and can usually be overclocked to more than 200 MHz, so timing-wise it looks promising. Okay, let's build it. There is room for a female USB-A connector on the PCB, but to make use of it we have to use some short jumper wires to connect the TP2 and TP3 pins of the Pico to the corresponding pads on the board. The first thing I wanted to do with the ISA Blaster was to make it work like a USB mouse adapter card. This would allow me to use a USB mouse on an old computer without the use of an external USB to serial adapter like the ones I showed in a previous video. Whenever you move the mouse or press a mouse key, the mouse sends to the PC a couple of bytes describing the mouse state. The actual data in this communication varies depending on the mouse protocol, but these are relatively well documented. Since Microsoft serial mice are well supported in DOS, emulating such a mouse with the ISA blaster seems like a good idea. In a PC, the serial mouse does not talk to the ISA bus directly. Instead, it talks to the UART, which then talks to the bus. UART is a serial communication interface which in the early days used to be a standalone chip, the 8250, but then got integrated into Super I/O chips. A serial mouse in DOS works as follows. When the mouse moves, it sends data to the UART via the serial cable. The UART holds this data in a register and raises an interrupt. The CPU receives the interrupt and runs the mouse driver code that does an I/O read to the UART port to get the mouse data stored. The process repeats whenever there is data sent out by the mouse. So in short, the mouse talks to the UART and the UART talks to the driver. So in our case, the ISA blaster card would need to emulate a UART as if it were connected to a serial mouse, but in reality it would be connected to a USB mouse. The emulated UART would receive data from the mouse, it would raise the interrupt, and would then have to reply to any I/O reads performed by the mouse driver. Emulating a UART is not too complicated. There are just a handful of registers that need to have the right state, and one of them needs to be updated with the data coming from the USB mouse. So I implemented a UART interface in software, and it worked. Kind of. My virtual UART was being identified as a normal serial port by the BIOS, and it was listed as usual on system startup. I could talk to it just fine with I/O instructions. However, there seemed to be some timing issue and the mouse drivers would not work well with it. CuteMouse, which is an open source mouse driver for DOS, would completely fail to detect my emulated UART. I traced the issue down to a 16-bit I/O read, for which the processor actually performs two 8-bit reads back to back. There was so little time between the reads that the Pico would just miss the second one. So the driver would read bad data and would conclude that the UART was missing. Well, that was disappointing. I was not completely sure what the issue was though. It could be that the Pico's CPU is just too slow. Perhaps writing optimized assembly would fix the timing issues. Or perhaps the GPIO pins are just too slow. Or maybe there's some significant lag between the time you set a GPIO pin and the time it actually changes. I was not sure, so I decided to redesign the project. Instead of emulating a UART, I could modify the CuteMouse driver. This would make the communication to the ISA blaster a lot simpler, and if needed I could avoid back-to-back I/O reads in the driver code, which could make things work correctly. This is exactly what I did. I created a modified version of CuteMouse that I called Dirty Rat because it's a quick and dirty hacked mouse driver. And on the Pico side, I no longer needed to emulate the UART, I just needed some simple code that sends out the mouse movement data to the driver. For convenience, I'm using the COM4 I/O address of 2E8 hex and IRQ3, but we can make this configurable. Here's how it works. Whenever the USB mouse moves, a tiny USB library callback runs in the Pico and the mouse movement data becomes available. Next, this data is translated into Microsoft serial mouse format, which is what the mouse driver expects. Then the Pico raises the interrupt to notify the driver that the data is available. And finally, the driver reads the data from the Pico with an I/O read. Okay, let's try it out. Let's plug in the ISA blaster to the ISA slot. I'm using this riser card just to film it from a better camera angle. When we power the system on, the Pico's LED lights up. This means that the firmware is running. Let's plug in a USB mouse. As you can see, any mouse activity causes the LED to blink, which can help us with troubleshooting. Since we're using the same IRQ and I/O port as COM4, we need to disable that serial port. I'm disabling both just to be on the safe side. Now let's load the dirty router driver and do some testing. It's working great. In Monkey Island it seems to work okay, but there is something wrong. It seems that the left click will sometimes register as a right click. And I think that a click registers multiple times. The yes/no pop-up window disappears as if I left-clicked more than once. Anyway, yeah, there are still some issues that need fixing, but I think it looks promising. Okay, that's all for today. I am planning to make the project sources available as soon as I fix the issues and do more testing, so please stay tuned. In the meantime, feel free to share your ideas about how else we could use the ISA blaster or how we could improve it. I hope you enjoyed the video, and as always, thanks for watching and goodbye.